Hello, my name is Andrew Kucher, and today I am going to be solving problem 10.13 from the Fundamentals of Heat and Mass Transfer by Bergman and Levine. So, going to the problem just to show it. The problem statement is as follows. You essentially have a saturated ethylene glycol pool above a hot heated uh, plate of diameter 200 millimeters, which is maintained at 480 Kelvin. And the question is asking, what is the power requirement to maintain evaporation in the ethylene glycol pool above the plate? And what is that rate of evaporation from that power requirement? And also, what fraction of how close essentially is the power requirement to the critical heat flux, at which point the water will be kind of going past boiling and into the superheated range of the temperature curve. And here are all of the given parameters. So it gives the saturation temperature of ethylene glycol, the heat of fusion of the ethylene glycol, the liquid density of the glycol, the vapor density of the glycol, C, and the Prandtl number of the glycol, and also gravity, since that comes into a play for nucleation, um, which is one of the assumptions that this is going to be a nucleate boiling point, and obviously going to be steady state, not changing anything with time. There's a fluid surface contacts of CSF equals 0.01 and n of 1. And I already discuss what we're going to be finding. So there's only going to be one surface. Again, there's like a pool of eth ethylene glycol. I'm not a chemist. Um, so to get the energy required for the boiling, we're looking for QS, the QS double prime, the heat flux of the surface essentially. But the energy of boiling is equivalent to the heat flux times the area, and the rate of evaporation is equal to that energy of boiling divided by the heat of fusion. Now, using the equation 10.5 from the book, you get this, which is a very fun equation, but we have all the numbers to solve it. So it's just a matter of plugging in the numbers, this and this. Just to run through the equation though, we have gravity times, in this term here, we have gravity times the density of the liquid minus the density of the vapor over the Stefan Boltzmann's constant, and that's all square rooted. And then this term is the uh, CPL from up here of the ethylene times the temperature change, which in this case is T sat minus, as you can see here, T, I didn't know write down, well, oh, T surface. It's the temperature of the surface minus the saturation point of the fluid. And then times the Prandtl's number, heat of fusion, and the CSF of the fluid, basically. And then you multiply that by mu of L and the heat of fusion yet again. And the value you get out of this is 1.78 times 10 to the fourth watts per meters squared. And then times that by the area of the plate, which is a circle, surface area, you get the energy of boiling at 559.44 watts. And again, divide that by the heat of fusion to get the heat of fusion to get the, oh, sorry, give me a second. Sorry about that. I realized I made a mistake in my calculation for the rate of evaporation. That is 6.89 times 10 to the negative fourth kilograms per second. Not 6.89 kilograms per second. That's a bit fast. Um, so sorry about that. Uh, as for the critical heat flux, again, the point where it'll start going to superheated range, that comes from equation 10.6 in the book. This book again. And again, we have all the values. It's in a sense a more simplified version of this equation for the surface flux. Not much to really say about it. Run through plugging in the numbers, and then you get the critical heat flux at 6.77 times 10 to the fifth. And then when you divide the surface heat flux by the critical heat flux, you get 0.026, which is 2.6%. All right. Hopefully that was helpful.